In the depths of human history, darkness was once an absolute condition. Imagine a world where illumination meant flickering flames, where communication traveled no faster than a horse's gallop, where the invisible forces connecting our universe remained unexplored mysteries. Then came James Clerk Maxwell, a 19th-century physicist whose mathematical brilliance would illuminate our understanding of reality itself. Maxwell's groundbreaking work transformed our comprehension of the universe through 4 elegant mathematical equations that would become the Rosetta Stone of electromagnetic phenomena. These equations were not merely abstract calculations, but a revolutionary framework that would ultimately enable humanity's most transformative technologies. From the smartphone in your pocket to interplanetary communication systems probing the most distant reaches of our solar system, Maxwell's insights became the foundational language of modern technological civilization. His equations revealed something profound and counterintuitive. Electricity and magnetism, previously considered separate forces, were actually interconnected aspects of a single, fundamental electromagnetic phenomenon. Imagine waves of energy dancing and transforming, invisible yet omnipresent, carrying information and power across vast distances. Maxwell's work showed that light itself was an electromagnetic wave, traveling through the vacuum of space at a precise, calculable speed. Consider for a moment the everyday miracles we now take for granted. When you flip a light switch, instantaneously banishing darkness, you're witnessing the practical manifestation of Maxwell's theoretical insights. When radio signals transmit voices across continents, when microwave ovens heat food, when satellite communications link continents, all these seemingly mundane technologies are direct descendants of Maxwell's revolutionary understanding of electromagnetic waves. These mathematical descriptions were more than academic exercises. They were a key that unlocked humanity's potential to understand and harness electromagnetic radiation. Maxwell predicted the existence of radio waves before they were experimentally discovered, demonstrated that light was an electromagnetic phenomenon, and provided the theoretical groundwork for future innovations in telecommunications, electronics, and our understanding of the universe. As we stand on the shoulders of this scientific giant, we can appreciate how 4 mathematical equations written in the 19th century would ultimately enable humanity to communicate across planetary distances, explore the cosmos, and illuminate the darkest corners of our world. Maxwell's work was not just science, it was a profound act of human creativity that expanded the boundaries of what we believed possible. Before James Clerk Maxwell's groundbreaking work, the scientific community viewed electricity and magnetism as entirely separate and unrelated phenomena. Physicists of the early 19th century understood electrical charges and magnetic fields as distinct forces with no apparent connection between them. This conceptual divide was similar to speaking 2 completely different languages, unable to recognize their underlying linguistic roots. Maxwell's genius lay in recognizing the profound interconnectedness of these seemingly disparate forces. He demonstrated that electricity and magnetism were not independent entities, but rather different manifestations of a single, more fundamental electromagnetic phenomenon. This unification was as revolutionary as discovering that 2 apparently unrelated languages actually stemmed from a common ancestral tongue. To understand this relationship, consider the dynamic nature of energy transfer. Imagine a river's complex system of currents and eddies. Just as water in motion creates intricate patterns and secondary flows, Maxwell showed that changing electric fields generate magnetic fields, and conversely, changing magnetic fields produce electric currents. This reciprocal relationship became the cornerstone of electromagnetic wave theory. The analogy of fluid dynamics provides an intuitive glimpse into this scientific breakthrough. In a river, water's movement creates swirling patterns that are interconnected and mutually transformative. Similarly, Electromagnetic fields exist in a constant state of dynamic interaction. A changing electric field doesn't just exist in isolation. It necessarily generates a magnetic field, and this magnetic field can then induce electrical currents. This perpetual dance of energy transformation is the fundamental mechanism underlying electromagnetic waves. Maxwell's equations revealed this intricate relationship mathematically, showing that electric and magnetic fields are two aspects of a single electromagnetic field. This was more than a theoretical abstraction. It provided a unified framework for understanding how energy propagates through space. Light itself was revealed to be an electromagnetic wave, traveling at a constant speed determined by the fundamental properties of electricity and magnetism. The practical implications of this discovery were enormous. It explained phenomena that previously seemed mysterious: how radio waves could travel through seemingly empty space, how light could propagate across vast cosmic distances, and how different forms of electromagnetic radiation, radio waves, visible light, X-rays, were fundamentally connected. By treating electricity and magnetism as interconnected forces, Maxwell opened the door to technological innovations that would transform human civilization. His work laid the theoretical groundwork for technologies we now take for granted: radio communication, telecommunications, electrical power transmission, and our understanding of how energy moves through the universe. This unification was a pivotal moment in scientific history, a beautiful example of how deep observation and mathematical reasoning can reveal the hidden, elegant connections that underlie the natural world. Maxwell didn't just describe two forces. He uncovered a fundamental language of nature, showing how seemingly different phenomena are part of a more profound, unified system of energy and interaction. Gauss's law for electricity represents a fundamental principle in understanding how electric charges distribute and interact within electromagnetic fields. At its core, the law describes how electric charges generate electric fields, revealing the intrinsic relationship between electrical charge and the space surrounding it. Imagine love as a metaphorical representation of this electromagnetic principle. Just as love radiates outward from a person, touching everything around them without discrimination, electric charges similarly create an invisible field that extends in all directions. This field permeates the surrounding space, influencing everything within its reach, regardless of distance or direction. To visualize this concept, consider a simple experimental demonstration using charged balloons and small pieces of paper. When a balloon is electrically charged, it creates an electric field that extends beyond its physical surface. If you bring this charged balloon near lightweight paper fragments, those fragments will be attracted or repelled based on the balloon's electrical charge. This phenomenon illustrates how electric fields interact with matter, showing that the influence of an electric charge extends far beyond its immediate physical boundaries. Mathematically, Gauss's law states that the electric flux through any closed surface is directly proportional to the total electric charge enclosed within that surface. In other words, the number of electric field lines passing through a surface reveals information about the charge contained inside. This law is crucial because it provides a way to calculate electric fields by understanding the distribution of electrical charges. The law introduces several key scientific insights. Electric charges are the source of electric fields. The field's strength depends on the total charge enclosed. Electric fields can pass through various materials with different properties. The distribution of charge determines the field's characteristics. Practically, this principle explains numerous phenomena, from how lightning forms to how electronic devices function. It helps scientists understand how electrical charges behave in different environments, from microscopic circuits to massive atmospheric electrical systems. By revealing the fundamental relationship between electrical charges and their surrounding fields, Gauss's law for electricity provides a profound window into understanding how energy and matter interact at the most fundamental levels of physical reality. Gauss's law for magnetism represents a fundamental principle in electromagnetic theory that explores a fascinating characteristic of magnetic fields. Unlike electric charges, which can exist in isolation as positive or negative, magnetic fields always appear as dipoles, with a north and south pole that are intrinsically connected. The law's most profound insight is elegantly captured by the analogy of a pearl necklace that can never be broken into single, isolated pearls. Just as each pearl in a necklace is inherently connected to others, magnetic fields always exist in closed loops, with magnetic field lines never beginning or ending in isolation. This principle is dramatically demonstrated through the concept of magnetic monopoles, theoretical magnetic charges that would exist as either pure north or pure south poles. Despite extensive scientific search, no magnetic monopole has ever been discovered in nature. Every magnet, from the smallest compass needle to the Earth's massive magnetic field, always displays both north and south poles intrinsically linked. Mathematically, Gauss's law for magnetism states that the total magnetic flux through any closed surface is always zero. This means magnetic field lines enter and exit a surface in perfectly balanced quantities, creating a closed-loop system. The law essentially declares that magnetic fields are fundamentally different from electric fields. They do not originate or terminate at points, but instead circulate continuously. This principle has profound implications for understanding electromagnetic phenomena. It explains why cutting a magnet always produces two complete magnets. It reveals the fundamental symmetry in magnetic field behaviors. It provides insight into how magnetic fields propagate through space. The law's implications extend from microscopic quantum interactions to massive cosmic magnetic phenomena, demonstrating the elegant, interconnected nature of magnetic fields across different scales of existence. Faraday's law of electromagnetic induction represents a pivotal discovery in understanding how electrical energy can be generated through motion and change. Imagine a water wheel where flowing water's movement transforms potential energy into mechanical rotation. Similarly, Faraday discovered that changing magnetic fields can generate electrical current, a process fundamentally similar to water driving a wheel's motion. The law states that a changing magnetic field within a closed electrical circuit induces an electromotive force, voltage, proportional to the rate of change of that magnetic field. In practical terms, this means moving a magnet near a coil of wire or changing a magnetic field around a wire will generate an electrical current. Your mobile phone charger brilliantly demonstrates this principle. Inside the charger, transformers use electromagnetic induction to convert high-voltage alternating current from wall outlets into the precise lower-voltage direct current needed to charge your device. Coils of wire surrounded by changing magnetic fields produce the electrical current that ultimately powers your phone's battery. Key aspects of Faraday's law include: electrical current is generated by magnetic field changes. The induced voltage depends on the speed of magnetic field variations. The principle enables electrical generators, transformers, and countless modern technologies. It explains how mechanical motion can be converted into electrical energy. This law bridges mechanical and electrical domains, revealing how energy can be transformed between different forms, a fundamental insight that powers our technological civilization. The Ampere-Maxwell law represents the crucial missing piece in understanding electromagnetic wave propagation, bridging the gap between electrical currents and magnetic fields. André-Marie Ampère originally described how electrical currents generate magnetic fields. James Clerk Maxwell's brilliant contribution was adding a revolutionary concept. Changing electric fields can also generate magnetic fields, even in the absence of physical current. This insight, known as the displacement current, completed the electromagnetic puzzle. Maxwell's mathematical elaboration revealed something extraordinary. Electromagnetic waves could propagate through empty space at the speed of light. This theoretical prediction was groundbreaking. By modifying Ampere's original law, Maxwell mathematically demonstrated that electromagnetic waves could exist independently, traveling through vacuum without requiring any material medium. The implications were profound. Maxwell predicted the existence of radio waves before they were experimentally discovered. He showed that light was an electromagnetic wave. The law explained how electromagnetic energy could transfer across vast distances. It provided a unified theory of electricity, magnetism, and light. By introducing the displacement current concept, Maxwell transformed our understanding of energy propagation. His work explained how electromagnetic waves could travel through space, enabling future technologies like wireless communication, radio transmission, and our understanding of cosmic electromagnetic phenomena. This law was not just a mathematical abstraction, but a fundamental breakthrough that opened the door to modern telecommunications, revealing the hidden mechanisms by which energy moves through the universe. Maxwell's mathematical calculations of electromagnetic wave propagation led to an astonishing discovery. The theoretical velocity of these waves precisely matched the known speed of light. This wasn't mere coincidence, but a profound revelation that light itself was an electromagnetic wave. By calculating the electromagnetic wave velocity using only electrical and magnetic constants, Maxwell demonstrated that light was not a mysterious phenomenon, but a predictable electromagnetic phenomenon. His equation showed that electromagnetic waves travel at approximately 792,458 meters per second, exactly the speed of light measured by contemporary scientific instruments. This discovery had revolutionary implications. Light was definitively proven to be an electromagnetic wave. The nature of light was mathematically explained for the first time. A unified theory of electricity, magnetism, and optics was established. The foundation for understanding electromagnetic radiation was created. Maxwell's insight connected seemingly disparate scientific domains, revealing that visible light was just one small section of a much broader electromagnetic spectrum. His work paved the way for understanding radio waves, X-rays, and other electromagnetic radiation, fundamentally changing our comprehension of energy and matter. This mathematical prediction was a landmark moment in scientific history, demonstrating how theoretical reasoning could unveil fundamental truths about the universe's underlying mechanisms. Maxwell's equations reveal how electromagnetic radiation generates and propagates stellar light. Stars produce electromagnetic waves through nuclear fusion, where charged particles interact, creating oscillating electric and magnetic fields. These interactions generate photons across multiple wavelengths, explaining why stars shine and how we can detect their radiation across vast cosmic distances. Black holes, despite being invisible, emit powerful electromagnetic signatures through their intense magnetic fields. As matter falls into a black hole, it becomes superheated and ionized, creating massive electromagnetic emissions. Maxwell's equations help scientists understand how these charged particles generate detectable radiation, allowing us to map black hole boundaries and interactions through radio telescopes and specialized electromagnetic sensors. The Sun communicates with Earth through multiple electromagnetic wave channels. Visible light, direct radiation providing energy and illumination, solar wind, charged particle streams interacting with Earth's magnetic field, radio waves produced by solar flares and coronal mass ejections, X-ray and ultraviolet radiation, revealing solar surface dynamics. Maxwell's equations explain how these electromagnetic waves traverse the 150 million kilometer distance between Sun and Earth, demonstrating how energy and information transfer occurs through fundamental electromagnetic principles. Maxwell's equations transcend mere mathematical formulas. They represent the fundamental language through which the universe communicates its most profound energetic interactions. These equations are not static symbols on paper, but dynamic descriptions of how energy flows, transforms, and manifests across cosmic and microscopic scales. From the breathtaking display of auroras dancing across polar skies to the intricate electronic signals enabling modern communication technologies, Maxwell's work provides the theoretical framework explaining how electromagnetic energy permeates and connects our reality. These equations reveal how light propagates, how electrical currents generate magnetic fields, and how energy transfers across seemingly impossible distances. The true marvel of Maxwell's work lies in its universality. His equations describe phenomena ranging from the tiniest quantum interactions to massive cosmic radiation events. They explain how stars generate light, how radio waves travel through space, and how electrical devices function at their most fundamental level. By unifying electricity, magnetism, and light into a single theoretical framework, Maxwell did more than solve scientific puzzles. He provided humanity with a profound understanding of the universe's underlying operational principles, a mathematical lens revealing the elegant, interconnected nature of energy and matter. As we continue exploring the cosmos, developing advanced technologies, and pushing the boundaries of scientific understanding, Maxwell's equations remain our most reliable guide, illuminating the hidden pathways of electromagnetic interactions that shape our existence.